Hello and welcome back. So this video is for class 12 and today we will start with a new chapter, that is magnetism and matter. So in the previous chapter we have seen that the origin of a magnetic field is a circulating charge. In this chapter we will focus on the phenomena of magnetism. Okay, we will try to understand the concept of magnetic field and the concept of magnetic field lines. Okay, so let's begin. First, let us discuss on what we know. So we know the concept of magnets, right? We know that magnets can be either natural or they can be artificial, right? Natural magnets, basically we get it from the earth. Okay, there is a ore called as the magnetite, and from that we can get natural magnets. Natural magnets, obviously they look just like rocks. Okay, they don't have a very good shape, correct? And even the magnetization, the field of these natural magnets is little bit less, correct? And then we have the artificial magnets. So generally magnets like the bar shaped magnets or the horseshoe magnets, or even some of the magnets that nowadays you get in the toy shop. Okay, these are the artificial magnets. Artificial magnets, they are made up of magnetic material. Okay, we put them in a very strong electromagnetic field, right? And that is how we are able to magnetize them. Okay, these are the artificial magnets. Artificial magnets can be made in various type of shapes and sizes. Most of the magnets, in fact all of the magnets that you must have seen, they are all artificial magnets. Next we know that the magnet, any kind of magnet will have two poles, the north pole and the south pole. Then we know that if we bring two similar poles, they will repel each other. So if we bring the north pole close to a north pole, there will be repulsion. Or if you bring south pole close to another south pole, there will be repulsion, correct? But if there is a north pole close to a south pole, there will be attraction. So again, this property is known to us that like poles repel and unlike poles attract. Okay. Next, what we know that magnet, any kind of magnet will always have these two poles. Means if you take a magnet, okay, it will have a north pole and a south pole. You cannot have a magnet that has got a single pole, that is a monopole, right? Even if you take a magnet and you break it into two pieces, you will get again whatever that piece is there, that piece will still have a north pole and a south pole. Okay, so again that is another thing to remember, that magnet always exists in dipoles. There is always a north pole with a south pole. You can never separate these poles. Okay, and then next we know that for any magnet there will be a magnetic field around that magnet. Okay, and then how do we understand the presence of this magnetic field? We see that if you bring any kind of magnetic material, for example a small piece of iron. Okay, so we will see that if I have a magnet and we bring a small piece of iron, the iron will stick to the magnet. Okay, so by that we will know there is a magnetic field around it. Okay, so these are the general things that we know about magnets. Now let us talk about the magnetic field and the magnetic field lines. Here we see a bar magnet. Okay, so in this magnet you see that this is the north pole and here is the south pole, and these lines, these are called as the magnetic field lines. Okay, what are these magnetic field lines? The magnetic field lines will give a representation of the magnetic field. So what you understand, these field lines will tell you that around this magnet over here, this is where we have the magnetic field present. So if you take any kind of magnetic material means a material which is attracted to a magnet. Okay, so if you take a small pin, okay, a small pin, if it comes close to this magnetic field lines, it will get attracted to the magnet. Okay, so here we have these field lines. Let us see the properties of these field lines. The first thing you will remember, magnetic field lines, these are continuous and closed loops. Okay, so these are closed loops that we are seeing. Then they will always move from the north pole to the south pole. Okay, that is the second property. Next we know that for these field lines, the direction of magnetic field will be given by a tangent. That means at this point, if I make a tangent like this tangent gives direction of magnetic field at this point. Okay, and you can see that the tangents will keep on changing like this. So that means the direction of magnetic field is also changing. Okay, so the next property is that tangent to the field line gives the direction of magnetic field. Next property, the magnetic field lines will never intersect each other. Okay, very important to understand. Every field line, it goes on its own path. Two field lines will never intersect. Why? If they intersect, then the magnetic field will have two directions, which is an impossibility. Therefore, we know that magnetic field lines never intersect each other. Okay. Another property is that the density of the field lines will give the strength of the magnetic field. Means, if you notice this area, you will see that many field lines are there. So there are more field lines. This means the magnetic field is more strong in this area. But here you will see the field lines are farther apart. Okay, the density is very less. That means here the magnetic field is lower. Okay, so the density of field lines will give the strength of the magnetic field in that area. So these were the properties of the magnetic field lines. Okay, remember them. They might be asked in the exam. Now we know that a magnetic needle, magnetic compass. Okay, it is nothing but a very thin magnet that is suspended at one point where it can rotate freely. And of course we know that if we take a magnetic compass, it will always point to the north direction, that is the north of the earth. Why it does that? It is because our earth is also a magnet. Okay, our earth has a magnetic field that goes around the earth. Okay, direction of the earth's magnetic field is from the south pole to the north pole. So when we take any kind of magnetic compass, it always aligns itself along the magnetic field lines of the earth, and that is why it is able to show, always able to point to the north direction of the earth. Okay, so if we take a magnetic compass, okay, and if we bring it close to any kind of bar magnet like this, we will see that it will begin to turn. Okay, it is the magnetic needle is turning because of the magnetic field. The magnetic field is exerting a force on it. So we can actually find out the potential energy of this magnetic needle. Okay, it's a very simple formula. So we'll take a magnetic needle, okay, and then we will bring it inside a magnetic field. We will notice there will be some kind of turn, there will be some torque that is exerted. That will of course change the potential energy of our needle. So the potential energy of the needle will be given by Um equal to integral of torque, which is function of theta d theta. Here theta represents the deflection of that needle. Okay, by what angle it has got deflected. We know torque is given by M cross B. M is magnetic moment, B is the magnetic field. So we will get therefore this equal to integral of M cross B d theta. Correct? M cross B is nothing but MB sin theta. So we will get this as one thing I forgot to mention. We'll have to so we will get this as integral of MB sin theta d theta. Okay, MB are constants, it will come out of the integral. So we will get integral of sin theta d theta, which is minus cos theta. So therefore we will get this as minus MB cos theta. This is the magnetic potential energy of the compass. Of course, minus MB cos theta is nothing but minus M dot B. Okay, so the potential energy will be given by this formula. Next, we will see some formulae for magnetic field. Now, these we will accept without proof. Basically, we get this formula by seeing that magnetic field is analogous to the electric field. Okay, more explanation you will find in the notes. So, what is the formula? If we have a bar magnet, on the axis of the bar magnet, the magnetic field will be given by this formula. Okay, BA. Okay, to show that it is on the axis, BA is equal to mu naught by 4 pi 2m upon r square. M is the magnetic dipole moment of the magnet. R is the distance on which point we are measuring the magnetic field. Okay, so BA will be given by this formula. Next, for a point on the equatorial plane of the magnet. Okay, that is on this point. So on the point, for a point on the equatorial plane, magnetic field that will be given by B equal to minus mu naught M upon 4 pi r square. Here we are getting a minus sign. This minus sign will show that the direction of magnetic field will be opposite to the direction of the magnetic dipole moment. Okay. Now of course magnetic dipole moment, we know how to find the direction of the magnetic dipole moment. The direction of magnetic dipole moment will be from south to north. So in this case, the magnetic dipole moment is going like this, south to north. So for a point on the axis, the direction of magnetic field will be same as direction of dipole moment. But in the case for a point on the equatorial plane, direction of magnetic field will be opposite to the direction of the magnetic dipole moment. Okay, so these things should be remembered. Now I want you to look at solved examples 5.1 to 5.5. These are mostly theory based, and some of them are little bit you put a formula and you get the answer. Okay, very straightforward kind of questions. But take a look at these problems. These will help you to understand the formulae and the concept of magnetic field in a better manner. Okay. In the next class, we will look at the Gauss's law for magnetism, and then we will see the very important magnetic properties. Okay. So that's all for now. Thank you.